Welcome to the universe. Deoxyribonucleic acid, or DNA, is a fantastic little molecule. It is the blueprint for all life on Earth, all life as we know it. But I don't think you really can truly comprehend just how much information is packed into such a small space until you give some kind of example. That is our first topic today. So if you were to go into each one of your cells and you took the DNA and you stretched it out, you went into the chromosomes and you grabbed each end of DNA and you stretched out those few billion base pairs, it would equate to something about 6 feet long, about 2 meters. Coincidentally, how far you need to stay away from me at all times and other people. Anywho, about 6 feet or 2 meters. The recent estimates that we have on how many cells are in the human body is somewhere around 30 to 50 trillion. So many. And if you consider how many humans are alive right now, let's say around 7 billion, we can get a total amount of DNA all stretched out. And I like this example because it's very close to those examples you always hear. Well, what if you laid out all of your circulatory system, or you laid blue whales end to end? Well, you'd kill them and they'd reach space. You monster. But what would happen for something like DNA? I've never heard this example before. I got it from one of my facility staff members. And if you do the math, you find that you will create a chain of human DNA from all the humans living, about 3 pounds from each person. Oh, that's bacteria. No, it's 3 pounds. About 3 pounds of DNA from each person. Stretch it all out. If desyncing has happened, we're going to deal with it. Anyway, if you stretch this all out, then you get a line of human blueprint that is 400 million light years long. It's hard to express just how long this is. You know, a light year, the amount of distance that light will cover in 1 year, you know it's a lot. It's so much. It's like 10 quadrillion meters or something like that. So if we laid out end to end all the human DNA from everyone alive right now, watch my hand. It would go around the entirety of the Milky Way galaxy. If you imagine the Milky Way galaxy like a circle, and you take the circumference of that circle, the outside edge, all the human DNA would encircle the entire Milky Way galaxy 150 times over. There is so much information in your body, so much amazing microscopic machinery always ticking away inside of every one of your cells. It's amazing. And I just wanted to make you think of how much you'd die a couple hours after we did this. Once your body stops making the necessary proteins, it reads your genetic blueprint to see what proteins it needs to make to keep your body functioning. In a couple hours, you wouldn't be instantaneously dead if you took out your DNA, but it wouldn't end well for you. Welcome to Office Hours, my podcast version of the facility where I join you for an hour or so, take all of your nerdy questions, and we cover a number of topics. As you can see, there'll be some lag here and there in the facility. We haven't gotten fiber yet, Kevin! Sorry. But in the facility, the connection's not always great, so we're doing our best. There might be some audio syncing issues, but we're going pretty good. So I have your chat up on this fancy new monitor, which you'll be seeing very soon. And welcome, if I haven't seen you before. This is the facility. I am the administrator. Today we'll be going through a number of topics, as well as addressing many of your nerdy questions in the chat, which you can see right here. And spoiler alert, there's a new video going up tomorrow on the channel. I'm very excited. It's, I gotta say, might be my best one at the facility so far. I'm very, very excited about it. But before we get to answering your questions, what are we going to cover today? Well, we already covered galaxy DNA. We're also going to talk about lakes that kill people invisibly. We're also going to talk about bugs and what's happening to them. It's bad. We're also going to talk about one of the coolest demonstrations I've ever seen, a physics demonstration, one of my favorites I've ever seen about gravitational waves. So hopefully this one, if you've ever been confused about gravitational waves, hopefully this one will be more explanatory than most. And then finally, we'll end talking about, well, you know what we got to talk about. But first, you know I want to get to the chat. So what does the chat have to say? Gas legs. Oh, I should note, if you're watching live, I do have a security team in the chat. So if you are spamming, if you are posting anything bad, it's an instant ban. Because of the facility, I rule. With an iron fist. Which would weigh about 6 pounds, by the way. Yep, I know there's probably some audio sync issues. But that's just the facility's connection at the moment. In fact, maybe I can try to do something a little bit about that. Okay, so why don't we start looking at the chat? I think if I'm right, the audio is gonna catch up in a moment. Kevin Wu says, can you explain white holes and how we would theoretically find them? Well, good question, Kevin. I'm not an astrophysicist. I'm not a nothing. I'm just a science boy. But as far as I know, white holes are almost completely theoretical. Well, they are completely theoretical. We've never observed one. So unlike black holes, which were theorized about for decades and then provided actual visual confirmation, white holes have been theorized about but never observed. They are the theoretical opposite of a black hole. So instead of sucking everything in and never letting it return, it spews a bunch of stuff out. And it could have cool implications for physics and all that stuff, but one has not been observed as of yet. So it would be hard to go into the really specifics, especially with me not being an expert. What would it be, Jonathan asks a similar question. What would it be like to see, would you like to see what's inside a black hole even if it kills you? Oh, you mean the plot of Interstellar, kind of? Well, I think being near a black hole or observing one closely would be an amazing experience. And I think what's really fascinating about how they work is that consider you watch someone fall into a black hole. What happens? Well, they're going to be torn apart atom by atom as the tidal forces from gravity pull them apart atom by atom, because just the difference between the bottom of their shoe and 1 nanometer above their shoe, the gravitational difference is so great near a black hole that it will tear them limb from limb and spaghettify them. We need a better name for that. Let's come up with one at the facility. Make a note. Kevin! Make a note. But when someone falls into a black hole, something weird happens. Ask yourself, would you see someone get spaghettified? The answer is no. Because the light coming off of a person, if you're watching them fall into a black hole, light, think about it, light, just like the lights in the facility here, so bright. Whew, I'm coming in hot today. The lights are bouncing off of my face and going to you. So there's a reflection happening. Now, if a person was to fall into a black hole, that reflected light, what happens after they pass the event horizon, where light does not have the velocity to escape the gravitational influence anymore? Well, what would actually happen, is that you would see, however your friend crossed the event horizon, if it was like, oh no, that's the last image you would see of them. And it would stay that way, slowly fading into nothingness, because they might be getting spaghettified in the black hole, sure, but that light reflecting off of them to show you that spaghettification will never reach you. So you will see your friend, the last image you'll ever see of them is right when they cross the event horizon, and then slowly fading into nothingness, perhaps disassembled and put on the surface of a black hole like a hologram. But we don't have to get into that. Great question. Why do people squint? Someone just asked. Why do people squint? Well, it's because you can kind of approximate a pinhole camera and increase the resolution for what you're seeing, like a pinhole camera does. It's forcing light in through a certain aperture of a certain size. When you squint, you can kind of make your eyes a pinhole camera, and it'll barely increase the resolution of what you're seeing. So when when you're trying to see something far away or close up, or people with glasses, they take them off and then they need to squint. That's what's going on. Just a little bit of physics, just with your eyes. We're doing good today. A lot of good questions. Don't mind this. Why are some... Ross King, a staff member at the facility, if you want to join, you can go to patreon.com/Kyle Hill. We have over 1,000 people in there talking with me almost 24/7. It's fantastic. I love the support. Ross King says, why are some magnets stronger than others? Interesting question. So magnets, how do they work, is a fun question in and of itself. And Richard Feynman, genius, Nobel Prize winner, one of the people who worked on the Manhattan Project, he put it in a very cool way. So you know that your hand, unless you're trying to do something pretty dangerous, your hand normally won't pass through your other hand. I mean, I could force it through, and it'd be gross, and then I'd get demonetized. But everyday circumstances, you touch stuff, and it doesn't go through. I sit on a chair, I don't go through the chair. I touch the desk here at the facility, and my hand doesn't go through. Why? Well, that's because of electric repulsion. So all atoms have a cloud of probability that have electrons. Probability cloud of electrons around every atom, and those have a charge, a negative charge. And that's on everything. So when you try to touch two things together, when you get very close together, the forces get stronger and stronger and stronger. It's like the reverse of the inverse square. So when you get really close, they're really strong. And so that electric repulsion from the electron clouds doesn't let your hands pass through each other. Now we accept this, and I'm paraphrasing Feynman. I'm not awesome like this all the time. Just half the time. But what Feynman said is that we perfectly accept this every day. But then when we have something like a strong magnet, where we feel repulsion before we see contact, we're confused. But what magnets are doing, all of the atoms in the magnets are oriented in the same direction. So your hand is a jumble of spin everywhere. The properties of the atoms are kind of all over the place. But in a magnet, in a really strong magnet, in a magnet, all of the atoms and their spin, how they repel stuff, is all lined up perfectly lockstep. So if you have some material, some magnet that is weaker, maybe some are not in lockstep. There's some pockets within the magnet that aren't all lined up with its buddies. But when you have a really strong magnet, it's all lined up with its buddies. All the atoms are doing the same thing. And so that multiplies the normal electrical repulsion effect that we usually see. So magnets isn't some magical property at a distance. It is really just this extended out to here, because all of the atoms are lined up in just the right way. Doing pretty good on the questions, chat. But before we come back to the chat, we got to get to another topic. You know we do, which is this button. This button. This button. I learned about a new thing. And every time we venture to a new part of the facility, there's going to be some audio desync, so just bear with me, Kevin. I learned about a new thing. Hey guys, if you're spamming the chat and I'm not getting your question, there's a lot of people in here. You will be timed out or banned. Just be cool. Just be cool here. We're all nerds here, all right? So I learned about a new thing. It's called a limnic, like a limerick, a limnic eruption. Now I never heard about this until I saw something on Reddit. This is also known as a lake overturn. And what it is, it's a natural disaster where some reservoir of carbon dioxide is released, from some geologic or volcanic activity. There's pockets of gas underneath the ground. That's how we get natural gas, et cetera, et cetera. Carbon dioxide is suddenly released in mass to the surface. It bubbles up. And what you're seeing now is Lake Nyos, shortly after, it's in Cameroon, in Africa, shortly after a Limnic eruption. And this release of CO2 is so sinister, which is why we're talking about it. When you release CO2 in this way, a lot of it, because of the difference in density of the gases between a lot of concentrated CO2 and air and temperature and pressure gradients and all of this CO2 released will stick close to the ground, just hang on the ground without diffusing as much, or it takes a while, into the air. So after a limnic eruption, you have this invisible layer of very concentrated carbon dioxide, and you can't see it. We need carbon dioxide. We need carbon dioxide, of course, to continue living, and plants and animals need it, and it's part of your metabolism. But in high concentrations, like even not that high, like 3 to 5% of the air you're breathing, if 3 to 5% of the air you're breathing is carbon dioxide, you can quickly pass out and then asphyxiate, choke to death, and die. This has happened. There was a limnic eruption in Cameroon in 1984, and 37 people died just living nearby, invisible. A second eruption happened at a neighboring Lake Nyos, which you're looking at right now, and it released 80 million cubic meters of CO2. That's so much. I mean, I could do some math on it right now, but 80 million cubic meters. This killed 1,700 people and 3,500 livestock through asphyxiation. So consider this, an invisible wall of carbon dioxide bubbling up from some kind of geological event, spreading out across the ground. And you could see it if you try to pour like fog in the air or something like that, but an invisible reaper. It is absolutely terrifying. And what can you do? You just have to leave. There's no air for you to breathe. It's crazy. Limnic eruptions. Interesting. So we're once again going back to the chat. Forgive the stream delay. I see some of you getting deleted out there. Be cool. Be cool. Yes, Aunt Jede, I once saw a limnic eruption on the Discovery Channel. Yes, this is why I'm talking about this. I actually saw a GIF of it where there was a low-lying pocket of carbon dioxide, and the presenter, I think it was BBC or Discovery, but the presenter poured out some smoke, I believe, just into the air. And you see the smoke settle on top of this invisible reaper. It was wild. Is the facility music at the right volume? I don't want it to be overpowering, of course. And I know who to blame if it's too loud. What's NC Conroy, rather, asks, what's the weirdest shaped planet that could theoretically exist? Well, we went a little bit through this on an episode at the facility about hollow planets. And this is kind of a no-go in terms of a question. Not because it's a bad question, it's a great question. But it's because how we define planets automatically makes them spherical. So when an object is big enough to overcome the forces that hold the material together, and then the solids can move like liquids, for example. When something is so big that gravity will actually start crushing it down, that's how we define a planet. And the easiest way to conserve gravitational energy in all directions because gravity is pulling in from all directions, right? Well, if you pull something in from all directions, you form a sphere, or a spheroid, roughly spherical. So all planets are roughly spherical, to answer your question. If you wanted to have like a square planet, and I say roughly spherical, they can be, you look at an actual picture of the Earth, like geologically speaking, it's kind of squat. It's kind of smushed at the tops, and it kind of bows out at the sides, kind of like what's happening to all of us in quarantine eating too many snacks. So it kind of bows out at the sides, and that's because the Earth is spinning. And if you've ever been on a merry-go-round, when something spins, it kind of flings mass outwards, right? If it's not attached to something. And so the Earth's mass is being flung around, outwards from the equator, mostly, and that's why it bulges at the sides. Anyway, my point being, you're not going to get something like a square planet or a pyramid planet. Just a second, I just thought of a really cool name for an anime. Kevin, write down pyramid planet. What was I talking about? Yeah, so if you wanted something like a pyramid planet, it would have to be small enough to not be considered a planet. It can be absolutely enormous. The sides of the pyramid could be many kilometers across. It'd look planet-ish, but it's not so big that it collapses in on itself. So you could have really, really big objects like a Borg cube, and that's fine. But once you have the mass that a planet has, nature spherifies you. Hope everyone's doing well during these times. I wanted to start doing office hours. I should have said this at the top, but the reason I'm doing office hours is because I wanted to approximate what I really, really liked in college, which is when I had a fantastic professor who always challenged me and gave me things to think about. I always went to their office hours, and we chat for hours just talking about stuff. We became friends. I'm in touch with many of them. And so if I can be anything approaching that for you, then I want to. And so we are in office hours now. Javier Nicolas Busmante Correas asks, I did that pretty well. What's your favorite nature documentary? I don't know. I haven't seen very many lately. I think it's just hard to beat Planet Earth. I mean, for the scale, and Planet Earth 2 and Blue Planet, for the scale of what they did, filming over many, many years with the top-of-the-line equipment, filming some of the, hardest to find phenomena, whether it be, filming endangered cats, in the mountain ranges, snow leopards, or it's trying to catch, the bloom of flowers after a flood in a desert that only happens, once a year, or however long, whatever the period is. To capture that, put it all in HD, it's just phenomenal. It's very hard to beat. I mean, the deep sea episode, when you first see the vampire squid, I remember sitting in front of my television, not even on the couch, sitting up close in my television, and literally just going wow, absolutely fantastic. Deadly Dex asks, could an alien race force a planet into a cube shape? Well, you would have to artificially make this planet. So I think either you change the force of gravity acting on it, which seems like a tall order going against physics, or you literally geoengineer the planet with more robust structures that can handle the gravitational forces. I don't know what that would be, but I'm talking about ultra material, like the way that you would put rebar into concrete. So you'd stuff the planet with extra strength material, and then maybe you could adjust its shape. But I don't know what that material would be, and the forces still might be too much. You'd have to do the math on that. Philosophical Questions asks, is there a lot of communication among science communicators and educators? I mean, that's a fun question. In fact, let's go to you right now. So, Philosophical Questions, is there a lot of communication among science communicators and educators? Yes, there's so much. I mean, aside from the occasional conference, YouTube had one that was really nice called EduCon that I went to, where like 400 educational YouTubers met up, and it was great to meet, Vsauce, Michael from Vsauce, and Diana the physics girl, Joe Hansen, It's Okay to Be Smart, Nessie Hill, who we've talked about before on the show. But aside from conferences, and aside from a few of the big YouTubers you probably watch that live, like Destin will live in Alabama, Texas. Anyway, there's a few remote people. What I mean to say is a lot of the people that you know and love and you watch on YouTube all live in the same city, and we all talk to each other, and we go over to each other's houses and have fun and stuff. I guess I won't name names because I don't know if they want me telling you that they all live in the same city or what city they live in, but yeah, a lot of us are friends. I've babysat Veritasium's kids. Derek is a really good friend of mine. We're all friends, and everyone, even if you're not friends, everyone's very fast friends. We're all doing the same thing, trying to figure out our own business through this, and it's funny too, and kind of frustrating because whenever you go to like something aside from YouTube, if you want to go to an audition for like a television show, we're like, hey, we're looking for a fun sciencey person. We see each other all the time, and you walk in the door, and it's like 4 other people that you know very well and that are your friends, and you're like, I have to compete against her. She's so good, and I want her to get it, but I really don't. But I do. So it's complicated and fun. American Mapper says, hey, do you know Scott Manley by chance? I do not. Last interaction I had with him, he subtweeted me on Twitter. So, seems like a nice fellow. I like his voice. But the last thing he said to me, I tweeted some facts out. He's like, that'd be interesting if I didn't already know those facts. Okay. Seems nice. Don't message him. We do not know each other. Mark Cochran says, science YouTuber tournament arc when? I'd love to do that. If you go watch Matt Pat's live stream for St. Jude, which is a couple months ago, he raised like $1 million in 10 hours. Absolutely fantastic. But a couple hours into the live stream, which is still up on his channel if you want to watch it, they did a trivia challenge between Matt Pat, his wife, Stephanie, Matt Pat and his wife versus me versus Vsauce 3. So we did do something like that. If you want to see who won, spoiler alert, it wasn't Matt. And with that, son of a gun. With that, bugs, love them or hate them, they are integral to the survival of the ecosphere. There are so many insects on the planet, they outweigh the total biomass of insects on the planet far outweighs the biomass of humanity. In fact, all the insects put together, if you weighed them on a scale, it would outweigh humanity 17 times over. So there's a lot more bugs. They pollinate plants, they're food for other organisms, they're critical at almost every level. But something's been happening to them. Something bad. Recently, a report came out based on 73 studies. Over the last 50 years, 50% of the insects are gone. Now, just let that sink in for a moment. I'm not talking about 50% of a certain species. I mean, literally, 50% of the bugs are gone. And look at how gorgeous he is. Or she. Or it. 50% of the insects are gone. This is a looming apocalypse. If the insects go, a lot of other things are going to go. And this is, of course, because of human encroachment, deforestation, climate change, pollution, loss of habitat, those kind of things. So in the last, not even in a century, about I mean, if you average it out, it didn't happen in an average way, but each year we're losing 1% of insects. And even if you don't like bugs, bugs are critical to the functioning of the biosphere, like we said about pollination and what have you and what have you. Just being part of the food web, that's very important. We've lost 50% of bugs. I don't have a whole lot else to say about it other than I wanted to make you aware of that fact. And the next time that you see a little spider or a little ant somewhere, don't crush it. It's trying to survive. It's just trying to survive. Back to chat. Been going about a half an hour so far. How's everyone's day going? Um, 94 Dodge Dude says, confirm Kyle is a Pokemon bug trainer. Nah. Well, I haven't played a lot of the most recent games I played were Sun and Moon. And before that, it was like literally Red and Blue and Silver. So I haven't played a lot of Pokemon recently. I have another nerdy hobby that takes up all my time, which many of you will know. But look, if you're Gen 1, you gotta run a Kadabra. You gotta run a Kadabra. You gotta run a Lapras. You gotta get that Surf. I'm a Blastoise man. Hydro Pump comes in very handy. But honestly, just a high-level Kadabra gets you pretty much one-shotting all the way through the Final Four. Or whatever they call themselves. Kadabra. I was so obsessed with Kadabra. I lived in China for a couple of years, and I lived in China as Magic cards came out. So you can imagine it was kind of crazy. I was so obsessed with Kadabra, I stole a kid's Kadabra Pokemon card from his backpack in the middle of class, and I took it. And I never felt good about that. Don't steal. Brian Upshur says, how do you feel about the Russo, not Russell, Russo brothers directing a Magic the Gathering TV show? Well, hell, have you seen Infinity War? I mean, Infinity War and Endgame, I mean, those were really, really, really fun movies using really complicated lore. So if they can take the really complicated lore of Magic the Gathering and turn that into a really, really fun movie, especially if the rumor that I saw yesterday was true that they are looking to cast Scarlett Johansson, like she could be like a Chandra or something like that, then, I mean, it might be awesome to take a very niche, nerdy thing and extend it out to a wide audience. I would love to have more people playing Magic. More people for me to beat. Mark Cochran says, daily reminder that you could eliminate all mosquitoes from the face of the earth with absolutely no ecological impact. We've researched this. I do not think that's true. I think there might not be like a big difference to us, perhaps, but you're still messing with the food chain. There would still probably be knock-on effects to like bats, for example, who eat mosquitoes by the truck ton. Truckload? Ton truck. Crin Firelight says, spiders are not bugs. Correct. So if you see a spider, just leave it alone. It's not a bug. It's an arachnid, of course. 8 legs, 2 body segments instead of 3. Insects have 3. Spiders have 2. Crin, you reminded me of a fact that I was going to say, which is unrelated to insects. Thank you. But spiders eat the equivalent biomass each year as humans weigh. Just in, discarded, their main sources of food and then discarded food, blah, 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 blah. Yeah, so if spiders became huge, well, they'd have different metab. If spiders preyed on humans, each year they would wipe us all out. Think about that. Thorandor says, is there any benefit to having completely chemically inert hair? Like glass. Like having glass hair. If I had shards of glass hair, I would look like Goku. Anyway. The funny thing is... Who asked that? I lost you. The funny thing is, whoever asked that question, is that your hair is pretty much inert. Despite what the beauty companies will tell you, your hair itself, your hair doesn't absorb stuff. It's protein. Quote me on this. Your hair is protein that has been Play-Doh pressed out of the follicles in your scalp. Once it gets out there, it's just protein. Protein is dead. It's not alive. You can put stuff on your hair to make it a different color or more shiny, like argan oil. Not a sponsor. But your hair itself doesn't absorb anything. If you wanted to change how your hair was growing or how healthy your hair was, you could massage stuff into your scalp, and it might make its way into the follicles via the skin and absorption. Or you change your diet and, you have vitamins or what have you, and that makes its way to the growth of the hair. But your hair is pretty much dead and inert as it is. So yeah, I guess you'd be fine with glass hair if it grew out of your head. And if you see shampoo that's like these vitamins, you put them on your hair and it's going to make your hair better in the long term. That's not how hairs work. Protein is dead. Devil Ape 07 says, good evening. I live in Germany, so it's 1 a.m. right now. I appreciate the commitment. Dankeschön even. Damon Hat says, I'm way out of sync with audio. Oh, and then you got deleted. I was going to read your question, but that's what happens. And Skyfan12 says, how different would life be if humans didn't have opposable thumbs? You want to know a secret? I tried this once. I called it Life as a Raccoon. And what you can do if you want to... I'm sounding weirder as I say it. But what you can do if you want to see how life would be without opposable thumbs. Opposable thumbs is one of the great evolutionary changes that humans as a species went through, and our ancestors, apes, went through to really jettison us forward technologically and sociologically. When you can make tools, when you have what's called a precision grip on stuff, then you can make tools, you can build stuff. It's very important. If you want to see just how hard it is to live without thumbs and how life would change, live life as a raccoon like I did. Take your hand, take some tape your thumb to your hand, and then try to do stuff. You'll find that evolution was pretty good in giving us thumbs. Evolution doesn't have a will, mind you. When I say, evolution gave us something, or it's good that that happened to us, it's random. Evolution threw up a mutation that eventually, over generations and generations and hundreds of thousands, millions of years, gave us opposable thumbs through the lineage of, apes and mammals and stuff. It eventually gave us opposable thumbs, but when the mutations that eventually led to opposable thumbs came up, those mutations were random, and then they were selected for because whatever advantage it conveyed to the organism, it was more beneficial in that the organism could more reliably pass on its genetic information, and so those mutations became more prevalent inside of the population, and then you get opposable thumbs. But at no point did evolution say, opposable thumbs would be good. And at no point did evolution stop at humans and say, or at no point did evolution try to marshal more life towards intelligence. It's just what works. Intelligence works. Opposable thumbs work. Unless you be a raccoon and you tape them to your hands because you're a weirdo. If you do it, send me a picture of something broken. And with that, it's on to our next topic. Now this is the coolest demonstration of gravitational waves I've ever seen. So, you know me. I love a good physics demonstration, of course. And this one is absolutely fantastic. So this is demonstrating gravitational waves. So underneath this very taut sheet of semi-elastic fabric, you have 2 points pressing upwards on the fabric. Now, this is part of the physics demo that you've always seen when you take a very taut sheet like this and you put it down, and you put like a heavy weight and you put it down on it, and it makes a depression, right? So that is simulating how mass warps space-time. So this is just doing that in the opposite. It's pressing up, so it's still creating the warp in space-time. So this is analogous to how 2 point masses would be affecting space-time. And by spinning them around each other, this is trying to show how gravitational waves come about and how we would detect them. This would be a demonstration of, for example, 2 neutron stars orbiting each other, or 2 black holes orbiting each other very, 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 very quickly. And what you see is that at certain frequencies of this spinning, of this orbit, you do get a very noticeable standing wave. Right about there. So if you've always been, oh, look at that. It is absolutely fantastic. So if you've been confused, like me and like many of us, about how gravitational waves actually move through space-time, it's like this. When you have 2 masses that warp space-time enough and they're rotating around each other, you can have that gravitational influence radiate outwards as what look like, like acoustic waves or ripples on a pond. And then we use a detector, something like LIGO, Laser Interferometer Observatory. Gravitational Observatory, yes. So that just won a Nobel Prize, and what it does is it tries to detect these gravitational waves by having a very, very long tube, and the tube is completely evacuated of air. It's a vacuum, evacuated. Maybe that's why those two were... And inside this tube, there's a laser, and it looks like an L. There's a laser here and a laser here. Now that laser is super, super, super precise in measuring the distances between the ends of the tubes, and it bounces off mirrors and stuff. So if it's hyper precise, the thinking goes that if a gravitational wave were to come through LIGO, it would change the shape of things just a little bit. And if your detector is sensitive enough, you can detect this small change. And so that's what was done. That's what won the Nobel Prize for gravitational waves. And this is what was being detected. This gravitational ripple moving across space-time from black holes that collided billions of years ago. But of course, this is quite exaggerated. Everything creates a gravitational wave at all times when it's moving through space-time. You're creating a gravitational wave right now. Some of us make less than other people. That's just how math works. And with that, oh, you know what we're doing. We're going back to you. Heed says, so binary stars in orbit would theoretically produce gravitational waves. Sure. But like we just said, everything does. So while you hear about black holes merging or neutron stars orbiting each other, when you hear about those all the time in the detection of gravitational waves, it's because by the time these waves get to us, they are so faint that it's almost impossible to detect. So you need a really, really good instrument, which LIGO is, and then to make the chances of detecting an event higher, you want a really big gravitational wave. And so you get that from these cataclysmic events in space-time, like the merging of neutron stars or black holes smashing into each other. You could theoretically detect gravitational waves from me to you, but you'd have to have a detector so precise that it's either A, impossible to build, or B, and 2, not practical to build. Flower Power, and we're going to get to this in a second, but Flower Power says, is there such thing as a good virus? That's an interesting question. You know, viruses, what they do to us is they go into our cells and they hijack our DNA. And they use our DNA to make copies of itself. It's kind of brilliant, of course. But evolution didn't... We already talked about it. But what a virus does is it clips out some of your DNA and then it puts in some of its RNA, just half of DNA, half of the double helix, and it puts its DNA into your DNA and then it goes, yeet, and then it's kind of done doing its thing. But then our DNA, in its normal process of doing protein and stuff, and you can stretch it out to 6 feet, doing protein and stuff, when it's reading the DNA, it then comes across the viral DNA and it says, sure. And it makes a new copy of the virus. So it uses our own DNA against us. Now, I say that because there's viral DNA inside of all of our genomes. We can actually pinpoint the places. We have done when we sequence the human genome with the Human Genome Project and blah, 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 blah. But you can find virus DNA inside of the human genome that carries on through all of us. And that's because in our past, a lot of people got infected by something or the other, and that was just passed down. Now, I say that because there could be, I don't know for sure, but there could be a lot of viruses that infect us, alter our genome in some way, and don't cause any real symptoms. But their visit is etched on our blueprints. So that could be the case. I don't know of any virus that is good per se, perhaps in the way that you mean it. Is there a virus that infects you and then you're immune to something else? Well, that's vaccines. That's what a vaccine does. So we make sure we don't get the virus first. We take bits of virus or a dead virus and we give ourselves, we stress test our immune system to give our immune system antibodies to fight the virus the next time our body sees it. But I don't know if I cannot think currently of any virus that gives you some benefit after infection. That would be, I don't know if it would be advantageous for the virus. I don't know. There's always a balance. When you think about, of course, as we all are, when you think about pandemics and stuff, there is a balance between how transmissible, there we go, this is live, how transmissible a virus is and how deadly it is. If it's hyper deadly and hyper transmissible, it's going to burn through a population really quick and kill everyone so quickly that there's no one to pass on the virus and the virus dies out. That's not very good, evolutionarily speaking, for the virus. On the other end, if it's really non-infectious, then it's going to have a very hard time spreading. So evolution corrals viruses towards, some middle ground and some standard deviation of that middle ground between mortality rates, rather, and infectivity. But we'll talk a little bit more about viruses in a moment. How about right now for a moment? Viruses. This is influenza. And influenza has been likened to what we're going through now, of course. People are likening it to the seasonal flu. And I just want to go through a little bit with you. Why is it seasonal? Why is the flu seasonal? It's a good question, because we do know now, well, we have a good idea, just based on the genetics and the biology of what we're going through now, that this is probably going to also be a seasonal thing, where even if the curves flatten very much and people return to work and you don't have to wear a mask everywhere, there's probably going to be resurgences of this virus for years. Many years, if not indefinitely, because it will be seasonal, as they say. But what do epidemiologists mean when they say seasonal? Well, let's go through that. Think about the factors that affect how a virus can infect people and at what rate. So what would actually physically, physics-wise, biologically speaking, when do more people get infected? And what would lead to an uptick in infection so that you could say it's quote-unquote flu season? What is happening? And if you think about it a little bit, it almost makes perfect sense. So why do we see more infections in the fall and in the winter, like with influenza? Why do we see this, and why might we see this with what we're going through now? Well, think about your health. So a virus has to infiltrate you, right? To hijack your DNA and etch your blueprint. in the wintertime and in the wintertime, in fall, when it's cold outside, when you're undergoing stress, when air is really dry, you know, dry noses, you're wiping it, you might be in poorer health, relatively speaking, during winter or fall months. And if you're in poorer health, then you're easier to infect. And think about the sociology of humanity going on during those same months. You are probably more indoors in the winter season. In the fall, school season is starting. There are more humans closer together than at other times during the year, and this would increase the number of infections, pointing out those months of seasonality. There's also host immunity. So like your general health, your immunity might be related to, how you're interacting with the world, you know, when you're going outside, when you're interacting with people, the sociological factors that we talked about earlier. And one of the most convincing factors that I've seen is absolute humidity. And I like this example because it's pure physics. And you know I like physics. But humidity, you know, the amount of water content in the air, how does a virus transfer itself? It has to physically do so, right? It has to transfer from one person's body to another. And it just so happens that when there's more moisture in the air, more water vapor, that it's easier for a virus coughed out of a body or some bodily fluid or something, a sneeze or waving your hands around like a crazy person. It's more easier for a virus to be aerosolized in this vapor or hitch a ride on some of this vapor, you know, just adhere to some, you know, water molecule and float along the air into your body where it hijacks your DNA. So when there's more humidity in the air, it would be easier for the virus to transmit itself. And this would fall into very relatively narrow ranges of humidity, which would then, again, point to certain times of the year being more seasonal for a flu or for what we're going through now. So there's not a whole lot we can do about it, of course. We're going to be more inside more often in the fall and winter. And that being said, we can learn a lot from what we're going through now. We need to learn these lessons just in case the next one, which there will be, is much worse. So, you know, could we eliminate some seasonality for the flu and for what is happening now if we all, you know, agreed to social distance as much as we can, you know, over Christmas time and at Thanksgiving and when we're all traveling and we wore masks when we were traveling? It would probably help, and we would flatten the curve of seasonality. So instead of spike winter, spike fall, it would be more of a just background rate of infection. And make no mistake, seasonality doesn't mean you only get the flu in the winter or in the fall. People are always getting the flu, and people will always be getting what's happening now. But the background rate is minimal compared to the spikes, and our healthcare system can generally handle it. So you'd want the seasonal spikes to be chopped. That's what we're trying to do. I got it. I just got to get back to my lab. You know what I mean? We're back to the lab, of course. We are back to you in the chat. Kevin, why isn't this working on the hotkeys? Let's get back to you. Ray Hill, cool last name, said, we're not related, are we? Ray Hill says, when people talk about CRISPR and gene editing, does gene editing only work in fetuses or does it work in adults too? Good question. Let's zoom in on that question a bit. I was trying to use the transition to drink. Why aren't the doors need to go faster? Anyway. Gene editing, why it's so potentially powerful, is that, yes, it would work on adults too. And what you're doing is going into your DNA, much like a virus, and you're snipping out pieces of DNA with CRISPR Cas9 enzymes, clustered regularly interspaced short palindromic repeats, CRISPR, and you're inserting some DNA that you want expressed in the cells where you want them expressed. That doesn't have to be the whole body. It could be a certain piece of tissue or what have you. So say your eye was deficient in making some protein. You could inject some CRISPR delivery vector into your eyeball or wherever. And in your eye, those genes would be translated and then expressed via protein, and your eye might make that protein again, and then you can see better. I don't know. Just an example. So you can do that in humans right now. And you can do it in fetuses, and you would do that to see the full expression of what you're trying to do, right? So you can change the development. I'm not an expert, so I'm backtracking. There are probably things about the adult body that you can't change after you're born, and I mean specifically very morphological things. So things like the shape of your head, or how many fingers you have, or what eye color you have, something like that. You're probably not going to be able to get an injection that changes how many fingers you got, or something like that. But if you go in at the fetus stage or the blastema stage or something like that, then you could change how the fetus actually develops. And so you could change those more fundamental things. So yes, both fetuses and adults. The scary thing is, not so scary, but the thing that we have to be very careful about is that if we're editing DNA, those traits possibly conferred by the editing will be passed on. Just think about that from an ethical standpoint. Say you are a person and you have some procedure done, and then when you reproduce and have a child, that child, because it has your DNA, you and whoever the partner is, because it has your DNA, it will also probably express those traits. Now that may sound harmless, but really think about it. You are making a decision for a human that they didn't consent to. What if the child didn't want XYZ or didn't want to have that eye color, that whatever, So you're making an ethical decision to edit potentially, your whole line. That's nothing to be messed around with. Anyway. Couple more questions. I hope the sync hasn't been too bad. I really do apologize. Last stream was perfect. The one before that was perfect. I think in my area of the... Kevin! In my area, still waiting on... my connection has been really terrible lately, so if we're out of sync, I apologize for that, and maybe... whatever. Bill Murray says, being born is unethical then? No, there's a difference between, there's a difference between choosing and randomness, right? Up until this point in human evolution, what traits you conferred to your child and in what varying degree was all totally random. Within, if you have a certain trait, they're likely to have it or they'll definitely never look like XYZ, but within a certain range, it's basically random where, oh, she has her mother's eyes or what have you, That's basically random, and we as a society are fine with that. It's random. It's up to chance. No one is making a decision. What's possibly unethical is if you make a decision knowing what will happen to a person being born. See the two differences there? They're completely separate ethical things there. You're considering the possible well-being of someone versus leaving and directly affecting it versus leaving it up to chance. Those are two very different ethical questions. San Raiku says streaming infrastructure platforms have been taking large hits in the last couple days. Yeah, so I apologize. Yeah, that's true. Yesterday and even today, Twitch was going up and down, was having a lot of problems. So I apologize. I just hope it's watchable. Elvaro de Hoyos says, "Hey Kyle, love the show." Hey, it's just like that other show. What fictional metal or substance do you think would have the greatest impact in society or technology like vibranium? Well, I was just going to say vibranium. So I think I'm going to use a placeholder. Avatar introduced like unobtainium, and that's it's really lazy writing to call it unobtainium. But the idea that it's introducing is something incredibly, incredibly valuable. I forget if they use it like a power source. I don't care. Who cares? I think the most world-changing fictional substance or metal or what have you would be some kind of fuel. So you can pretty closely track the technological and sociological evolution of society by what kind of fuel they're using. Campfire, steam, very refined gasoline. Then what? There's fission nuclear power plants. But if you wanted to go with something fictional, imagine a material that had an energy density 1 billion times more than coal. So like uranium or plutonium, when you're splitting it, the energy density, how much energy per mass is already 1 million times more than coal. It's so much more efficient. If I fused all of the water in this awesome thermos, it would equate to more energy than an entire trainload of coal. Just this. So if you have a fictional substance or refine a substance that is even more energy dense than fission and fusion, I don't know, you're down on an atomic level there. I don't know what you'd be doing. But if you found an energy source that was more energy dense than fusion, that would completely change society. Well, fusion would already do that, but let's say we just found this fictional thing. By which I mean there would be no energy problems. You'd have basically unlimited energy. And what could you do with unlimited energy? Just think of the economic impact. How many industries would immediately change? But I mean, my mind is spinning. You can think about it. Like suddenly, every single person on the planet can power lights in their home. And if you're watching me, you can power lights in your home. You're very fortunate. But a lot of people, a good percentage of Earth's population lives in, dirt poverty. So just imagine energy sources that could suddenly uplift everyone to the same technological level for no money. I mean, people would of course try to privatize it, and whoever discovered it would probably be, murdered or something for money. But, if you did, hyper energy dense materials would basically a quantum leap, which, why do people say quantum leap? Quantum leaps are very small. So small I can't show you with my fingers. Anyway, the next step up from coal past fission would radically change society. Let's go with one more question. D Legend 06 says, "Hey Dad, I'm not your dad. And I'll never be. Ever." That voice kind of sounded like Solid Snake for a second. Okay, wait. Nanomachines. The Patriots. The world was split into two. After World War II, the world was split into two. Tastes good. Ow. Let's take one more really good nerdy question. Okay, so relating to nuclear power again, which I'd love to do a larger episode on, but Bob Smith says, "Hey Kyle, I'm a longtime fan of your shows and your hair. Thank you so much. So nuclear power uses heat and turbines to generate power, right? So in a way, isn't nuclear power just the end point of steampunk technology? Yeah, imagine how like weird you could look at a Ren Fair if you had your own nuclear reactor. So much steam. But yes, to your point, we're not getting energy directly from nuclear reactions. Rather, we're using entropy and we're transforming energy from one form to another. So we are using nuclear reactions. And these nuclear reactions, these little particles going very fast with some mass, they hit each other and they hit the rods that contain the nuclear material. And these rods get really hot. And we use these hot rods to heat water that surrounds the rods. That water gets so hot, it generates steam. We use that steam, we pressurize it, and we use it to turn turbines, which creates electricity. But yeah, nuclear steampunk, I think, is just Fallout. What did we do today? Well, we talked about a lot. We talked about how long all the human DNA would be. Whew. Almost lost at the finish line there. How long all human DNA would be. It would encircle the galaxy 150 times. That's immense. We also talked about limnic eruptions, fantastically scary invisible reapers. We also talked about the insect apocalypse that is currently happening, and you should be aware of it. In less than a century, we've lost half of insects. That's absolutely insane. And finally, we talked about why seasonal viruses are seasonal. I hope you enjoyed this episode of the Office Hours podcast. If you want to join the facility, join me, not just talk with me in the chat here, but talk with me 24/7 through Patreon, through our Discord. You can go to patreon.com/Kyle Hill. You can get your name on ARIA each week. You get behind the scenes updates. You get shows a day early. Everyone in the facility, all the facility staff members saw a new episode this morning. So you can get in there, but until then, I hope everyone is having a fantastic week. Please stay safe. Please stay healthy. Listen to expert advice. I hope the stream was at least listenable with the desync. If it's bad, just listen to it. It's a video podcast, sure. But be nice to each other, because this is all we got.